We start with Maxwell's equations in free space, in Gaussian units. The magnetic field can be written as the curl of the vector potential. Taking the second Maxwell equation and substituting in our definition of the magnetic field, we can see that the second Maxwell equation is satisfied as the divergence of a curl is zero. Using the same substitution on the third Maxwell equation, we get an expression which involves the time derivative of a curl. Rewriting this as a curl acting on a time derivative, we can use the linearity of the curl to get the following expression. We can now solve for the electric field by setting the bracket equal to the gradient of a scalar potential phi. This is because the curl of the gradient of a scalar field is zero. Substituting this electric field into the first Maxwell equation, we get to a point where we can distribute the divergence on two terms. The first resulting in del squared of phi. The second, we can put on the vector potential A. These potentials are not unique. By making a gauge transformation, we can change phi and A without changing the physical electric and magnetic fields. This freedom allows us to choose conditions, called gauges, that simplify calculations. The Coulomb gauge is one such choice. It requires that the divergence of the vector potential vanish. That is, del dot A equals zero. Continuing along, we get that the negative gradient of phi equals zero. Substituting this into our electric field expression, we see that the electric field is now only determined by the vector potential. With this electric field, we substitute it into the fourth Maxwell equation along with our definition of the magnetic field. The left term can be rewritten using the curl of a curl identity. And, since we are using the Coulomb gauge, we can once again set del dot A equal to zero. This leads to a differential equation of the vector potential. The solution to this equation is given in terms of exponentials. Here, omega is equal to kc. Using the Coulomb gauge condition, one can show that k and the vector potential must be perpendicular. That is, the electric and magnetic field oscillate in directions perpendicular to the direction of propagation. This allows us to write out the vector potential as a sum of modes with E hat k lambda being two unit vectors perpendicular to k. The two unit vectors correspond to two polarization directions. The wave cannot be polarized in the direction of propagation. The ak lambda of x and t contain the exponential functions. Also note that the ak lambda next to the exponentials are numerical coefficients and not functions of position or time. It is useful to take E hat k lambda as directions of circular polarization instead of linear. Then E hat k lambda is given by the following. Here, lambda equals plus minus is the polarization state, and E hat k1 and 2 are the linear unit vectors perpendicular to k. With these definitions, one can show the following properties, where we have introduced the delta function, which is 1 if lambda is equal to lambda prime and 0 otherwise. Now let us recall that the energy in the electromagnetic field is given by integrating the energy density over all space. And using our previous expression for the electric field from earlier, we can substitute in our vector potential. This gives an expression for the electric field. We can also take the complex conjugate as to get the magnitude of the electric field squared. We multiply the field with its conjugate. When we multiply these two together, we will get a lengthy expression that involves a sum over lambda, lambda prime, k, and k prime. We can use two simplifications when we integrate this lengthy expression. The first comes from the position dependence in the exponential. The terms highlighted in red will be multiplied together and then integrated, giving us a delta function with k and plus minus k prime. The second simplification comes from the identity in the top left corner. This gives another delta function involving lambda and lambda prime. This leaves us with a sum over only k and lambda. The integral over the electric field part becomes the following. Since the magnetic field is the curl of the vector potential, we can get an expression for the magnetic field and its conjugate. Dotting these together and taking the integral, we now have the second half of the energy equation. Now, notice that the only difference between the electric field and magnetic field expression is that they have opposite signs on the third and fourth terms. When summing, the total energy reduces to a sum of time-independent contributions from the individual modes. Now let us move on to a process called second quantization. Just as the physical quantities such as position and momentum are thought of as operators in first quantization. In second quantization, the fields themselves are quantized and are promoted to operators. To see how this works, let us start by defining creation and annihilation operators for bosons. Here, the tensor product symbols are the insertion and deletion operator. We need to understand Fock states. Fock states are quantum states that are elements of Fock space with a well-defined number of particles. They are built as tensor products of single particle states, symmetric for bosons and antisymmetric for fermions. Let us act upon our Fock states with our creation operator, starting from the vacuum state. Here, 1 is the tensor identity. Acting upon a general state, Ni, the psi-I tensor product brings another factor of Ni plus 1. We can do the same with the annihilation operator, where now a factor of Ni is pulled down. An important note, the annihilation operator acting on the vacuum state gives 0. We can now find the commutation relation of the creation and annihilation operator by acting upon a state. Let us also introduce the following postulate. The annihilation operator acting upon a state, Nj, gives 0 for I not equal to j. With this postulate, it is evident that if we act upon a state Nj with the commutator of Ai and Ai dagger, we will get 0. It follows that the complete commutation relation is then given by the delta function. Let's move on to energy quantization. We will quantize the electromagnetic field by promoting the vector potential to an operator. To do this, we need to have the eigenvalues of a Hamiltonian be the energy of the electromagnetic field we found before. For a general multiparticle operator, K, the eigenvalues should be given by the state's eigenvalues Ki, multiplied by the number operator Ni. We will make use of creation and annihilation operators to create and destroy quantized particles called photons. Let us now write the Hamiltonian with our energy eigenvalues and our operators. We have added an arbitrary constant E0, which will be useful later on. Let us slightly rewrite the Hamiltonian by introducing a factor of 1/2. We need to know whether these particles are bosons or fermions. In other words, do they have integer or half-integer spins? To do this, note that a rotation by an angle phi around the z-axis is done with the following operator. This is equivalent to a rotation matrix. If we rotate about the photon direction k, the linear unit vectors e hat k1 and 2 transform in the following way. Applying these to our full unit vector, e hat k plus minus, we eventually get back to the same unit vector multiplied by a phase factor e to the I phi. This tells us that the photon is a spin 1 particle. Had the photon been spin half, we would have picked up a 1/2 factor in the phase. Let us revisit the commutation result we had from earlier. It follows that reversing the order gives a -1, and then we can slightly rewrite it to get an expression for only A dagger multiplied by A. Now, using that result, we can substitute it into the Hamiltonian equation we had. In this case, we only substitute it into one of the terms, and we get the following result. Now let's compare our Hamiltonian with our classical energy of an electromagnetic field equation. If we define the vector potential operator as shown, then these two equations are identical with an additional 0-point energy given by E0. The 0-point energy is the energy of the electromagnetic field when there are 0 photons present. It is sometimes called the vacuum energy. It is an infinite number. To deal with this problem, some argue that only differences in energy are measurable, just like the concept of potential energy has been treated in classical mechanics. In all practical calculations, This is how the infinity is handled. But this is not the whole picture. The zero-point energy has a positive energy density. This is a problem in general relativity, which states that energy should produce space-time curvature. Even if one argues that there must be a maximum wave vector k, the energy density is still much larger than the observed vacuum energy density. It is off by around 10 to the 120. This is known as the cosmological constant problem. It remains one of the biggest unsolved puzzles in physics. Let us see how the zero-point energy manifests in a macroscopic system by looking at the Casimir effect. Suppose we have two large conducting plates separated by a distance d. We can calculate the change in energy between the plates when separated by d and when at infinite distance away from each other. If the z-axis is the one perpendicular to the plate faces, the geometry is such that we have a restriction on kz. Specifically, kz is n pi over d, where n is an integer. We can write down the vacuum energy of this situation, and, since the lengths of the x and y dimensions of the plate are large, the summation over x and y can be replaced with integrals. Taking the limit as d goes to infinity gives us the full potential energy function. The process to evaluate this integral is quite complicated, and so only the result is presented. Since the force is the negative gradient of the potential energy, we can get the force, per unit area, to be the following. This shows that two plates in a vacuum have an attractive force between them following 1 over d to the fourth power. At submicron scales, this becomes the dominant force between uncharged conductors. At distances of about 10 nanometers, this produces a pressure that is equal to 1 atmosphere. Let us try to visually understand what is happening. We have two conducting plates in a vacuum separated by a distance d. The field outside of the plates allows any mode from the zero-point energy. There are no restrictions in place. Inside the plate, however, not every single mode is allowed. The fields must vanish at the conducting walls. This is why there is a restriction on kz to be n pi over d. Because of this imbalance in modes, the two plates are pushed together with a force proportional to 1 over d to the fourth power.